Students, welcome to this new video presentation on the topic kinetic theory. In part 1, I will first introduce the topic kinetic theory, followed by study of molecular nature of matter, behavior of gases, and kinetic theory of an ideal gas. This is given in chapter number 13 of class 11 physics prescribed by NCERT. First come first, introduction. Boyle discovered the law named after him in 1661. Boyle, Newton and others tried to explain the behavior of gases by considering that gases are made up of tiny atomic particles. The actual atomic theory got established more than 150 years later. Kinetic theory explains the behavior of gases based on the idea that gas consists of rapidly moving atoms or molecules. This is possible as the interatomic forces, which are short-range forces that are important for solids and liquids, can be neglected for gases. The kinetic theory was developed in 19th century by Maxwell, Boltzmann and others. It has been remarkably successful. It gives a molecular interpretation of pressure, temperature of a gas and is consistent with gas laws and Avogadro's hypothesis. It correctly explains the specific heat capacities of many gases. It also relates measurable properties of gases such as viscosity, conduction and diffusion with molecular parameters, yielding estimates of molecular sizes and masses. So let us start. This is a fairly simple chapter but very interesting. Please listen to my lecture attentively and note down important parts. I welcome you once again. Molecular nature of matter. Richard Feynman, one of the greatest physicists of 20th century, considers the discovery that matter is made up of atoms to be a very significant one. According to Feynman atomic hypothesis, all things are made up of atoms, little particles that move around in perpetual motion. So, to repeat Feynman's atomic hypothesis, all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are little distance apart, but repelling upon being squeezed to one another. That means when they are apart, distance apart, then they attract, whereas when they come nearby, they will repel one another. The next theory was given by John Dalton. The scientific atomic theory is usually credited to John Dalton. He proposed the atomic theory to explain the laws of definite and multiple proportions obeyed by elements when they combine into compounds. The first law states that any given compound has a fixed proportion by mass of its constituents. The second law states when two elements form more than one compound, for a fixed mass of one element, the masses of the other elements are in ratio of small integers. Gay-Lussac's law. Gay-Lussac's law also is given early in 19th century, which states that when gases combine chemically to yield another gas, their volumes are in the ratio of smaller integers. So Avogadro's law or Avogadro's hypothesis. equal volumes of all gases at equal temperature and pressure have the same number of molecules. Avogadro's law, when combined with Dalton's theory, explains the Gay-Lussac's law. Dalton's atomic theory can also be referred to as molecular theory of matter, since the elements are often in form of the molecules. Then we will just define mean free path. The average mean free path is the average distance of a molecule can travel without colliding is called the mean free path. That is, the average distance traveled by a molecule without collision is called mean free path. The mean free path in gases is of the order of thousands of angstroms. The atoms are much freer in gases and can travel long distances without colliding. The mean free path in gases is of the order of thousands of angstroms. We will continue molecular nature of matter. For many observations in recent times, we know that molecules which are made up of one or more atoms constitute the matter. Electron microscope and scanning tunneling microscope enable us to see them even. The size of atom is about an angstrom, which is equal to 10 to the power of minus 10 meters. It is very small, which we are able to see through scanning or tunneling microscopes. In solids, these atoms or molecules are very tightly packed. Atoms are spaced about few angstroms, that is 2 angstroms apart. In liquids, the separation between atoms is about the same, is about 2 angstroms. But in liquids, the atoms are not as rigidly fixed as in the case of solids, and they can move around. This enables the liquid to flow. In solids and liquids, the closeness makes the interatomic force important. The force has long range attraction and a short range repulsion. As stated earlier, when the distance between the molecules or atoms is very far, then these molecules attract, and when they are nearby, they repel. The atoms attract when they are at a few angstroms but repel when they come closer. In gases, the interatomic distances are in tens of angstroms. The atoms are much freer in gases and can travel long distances without colliding. If they are not enclosed, gases disperse away. So if we do not keep the gases in a closed container, then the gases disperse away. The gas is full of activity and equilibrium and is dynamic one. In dynamic equilibrium, molecules collide and change their speeds during collision. Atoms are not indivisible or elementary. They consist of nucleus and electrons. The nucleus itself is made up of protons and neutrons. The protons and neutrons are again made up of quarks. Even quarks may not be the end of the story. Behavior of gases. Properties of gases are easier to understand than those of solids and liquids. This is mainly because in a gas, molecules are far from each other and their mutual interactions are negligible except when two molecules collide. Gases at low pressures and high temperatures, much above that at which they liquefy, approximately satisfy a simple relation between their pressure, temperature, and volume given by the equation PV is equal to KT, where P is the pressure, V is the volume, K is a constant, and T is a temperature in Kelvin, that is in absolute scale. K is a constant for a given sample, but K itself varies with the volume of the gas. That is, K is proportional to N. That is number of atoms. That is, K is proportional to N in this sample. We can write K is equal to N into small k, where the K is same for all gases, and this small k is represented by the symbol K subscript B, and it is called Boltzmann constant. Its value is practically found to be 1.38 into 10 to the power of minus 23 joules per Kelvin in SI units. Therefore, we can write that as P1 V1 by N1 T1, that is simplifying this equation 1, P1 V1 divided by N1 T1 equals P2 V2 divided by N2 T2, that is equal to constant, that is equal to KB Boltzmann constant K small k subscript B, because the value of K is same for all gases. Hence we relate them as P1 V1 divided by N1 T1 equals P2 V2 divided by N2 T2, which is constant. Let it be equation 2. Then now we will take up Avogadro's hypothesis. If pressure, volume and temperature are same or constant, then N is also same for all gases. This is Avogadro's hypothesis. The hypothesis says that the number of molecules per unit volume is same for all gases at a fixed temperature and pressure. That is, if temperature and pressure are constant, then N is same for all gases. Avogadro number is represented by letter N subscript A. That is, symbol is N subscript A. It is a number in 22.4 liters of any gas. Suppose we take gas whose quantity is 22.4 liters in a container. Its value Na is given by the number 6.02 into 10 to the power of 23, and this is called Avogadro number. Then we will define what is a mole. The mass of 22.4 liters of any gas is equal to its molecular weight in grams at standard temperature and pressure is called a mole. So mole is a mass of 22.4 liters of any gas at standard temperature pressure, and it is equal to the molecular weight in grams, and this mass is called a mole. Now we will recapitulate perfect gas equation. We have stated in equation 1 PV is equal to K into T. So here in that equation 1, the value of K is represented by mu into capital R. So PV is equal to mu into R into T. In this, let it be equation 3. In this equation, P is pressure, V is volume, mu is a mole. R is a constant, universal gas constant, and T is the temperature in Kelvin, or it is absolute temperature. So here mu equals the number of moles, that is equal to m by m naught equals n by Na. Let it be equation 4. Here R is equal to Na into Kb. Na is Avogadro number. K subscript B is a Boltzmann constant. So R is a product of Avogadro number and Boltzmann constant, and it is called universal constant. And practically it is proved that the value of R is 8.314 joules per mole per Kelvin. All this you have to revise and remember the values. In this equation 4, capital M is the mass of the gas containing n number of molecules. That is, if a gas whose mass is M has n molecules, and m naught is the molar mass and Na is the Avogadro number. Applying 3 and 4, we can write, applying equation, PV is equal to Kb into N into T. So pressure, volume, Boltzmann constant into number of molecules into absolute temperature, or it can be written as P is equal to dividing, if we are considering a unit volume, that is the put value of volume as 1, then P is equal to Kb into small n into T, where n is the number of molecules per unit volume. Let's analyze Boyle's law, Charles' law, and Dalton's law of partial pressures using ideal gas relationship. A gas that satisfies the relationship PV is equal to mu into RT, where P, V and T are pressure, volume and temperature. R is a constant and mu is a mole, number in mole. And if a gas satisfies this relationship, PV is equal to mu RT at all temperatures and pressures, then it is defined to be an ideal gas. Another useful form of the relationship is P is equal to rho into RT divided by m naught, where rho is the mass density of the gas and m naught is the molar mass. An ideal gas is a simple theoretical model of a gas. No real gas is truly ideal. The figure on the screen shows the relationship between pressure, which is given in atmospheres on the x-axis, and the parameter PV divided by mu T, that is joules per mole per Kelvin on the y-axis. The graphs are plotted for different temperature. Different temperature means for curve 1, T1 is kept constant and P and the relationship is in the gas equation is measured and plotted. So for T1 the curve is in this form, for T2 it is shown, and T3. Here T1 is greater than T2, which is greater than T3. As seen here, there is a departure from ideal gas behavior for a real gas at three different temperatures. Notice that all curves approach the ideal gas behavior for low pressures and high temperature. You see here for low pressures and high temperature they are nearly equal to the ideal gas. At low pressures or high temperature the molecules are far apart and molecular interactions are negligible. Without interactions, the gas behaves like an ideal one. If we fix the value of mu and T in the equation 5, we get PV is equal to constant. Keeping the temperature constant, if we keep the temperature constant, pressure of a given mass of gas varies inversely with volume. So that is, if mu r and T are constant, P is inversely proportional to the volume, and this graph is plotted in the second graph. And we can see here, this is the famous Boyle's law. This figure shows the experimental PV curves and the values for different temperatures. See, for 200 degree Kelvin, the graph is lowest and the red graph is for the high temperature 600 degree Kelvin. Therefore, this also shows that PV is equal to constant and T is temperature also kept constant. Without interaction, the gas behaves like an ideal one. If we fix mu and T in equation PV is equal to mu into RT, that is equal to constant, that is keeping the temperature constant, the pressure of a given mass of gas varies inversely with volume. That is, if we increase the volume, the pressure decreases. You see, the pressure is decreasing. Now we will examine Charles' law. If we fix in the equation PV is equal to mu RT, if we fix or keep the pressure constant, then in the relationship PV is equal to KT, that means if we keep P constant, V is proportional to the temperature. And the experimental TV curves are plotted in the graph number 3. This is the graph on the right hand side of the screen. That is TV curves for Charles' law. Then for carbon dioxide at 3 different pressures, compound compared with the Charles' law dotted lines, T is in units of 300 degree Kelvin and V in units of 0.13 liters. These are the parameters under which the experiment is conducted. Here, please note that P1 is greater than P2, which is greater than P3. That is kept constant for each curve. The values are shown here. Then, if you fix P, PV is equal to K into T, or V is proportional to T. Then finally, we will study the Dalton's law of partial pressure. Consider a mixture of non-interacting ideal gases, that is mu1 moles of gas 1 and mu2 moles of gas 2, etc. in a vessel of volume V at temperature T degree Kelvin, T Kelvin and pressure P. It is then found that the equation of state of mixture is given by the relation PV is equal to mu1 plus mu2 plus etc. into RT. That is PV equals mu RT and mu itself is mu1 plus mu2 plus mu3 etc. because the sample is a mixture of non-interacting ideal gases. Note that these are non-interacting gases. Let it be equation 7. Therefore, this equation 7 can be written as P is equal to mu1 into RT by V plus mu2 into RT by V plus etc. etc. Let it be equation 8. That is, we are dividing by V, both left hand side and right hand side of equation 7. Therefore, P1 will be equal to P will be equal to P1 plus P2 plus etc. etc. Let it be equation 9. Thus, the total pressure of a mixture of an ideal gas is the sum of the partial pressures. We next consider some examples which give us the information about the volume occupied by the molecules and the volume of a single molecule. Let us examine the cases. Before that, let us see that P1 in the equation 9, P1 is equal to mu1 into RT by V is the pressure that gas 1 would exert at, at the same conditions of volume and temperature if no other gases were present. This is called the partial pressure of the gases, and the law is, just we studied, is Dalton's law of partial pressure. So now let us take up some worked examples. Next we will study the kinetic theory of gases. First, kinetic theory of an ideal gas. Kinetic theory of gases is based on the molecular picture of matter. A given amount of gas is a collection of large number of molecules, typically of the order of Avogadro number, that are in incessant random motion. At ordinary pressure and temperature, the average distance between molecules is a factor of 10 or more, the typical size of a molecule. The typical size is 2 angstroms. Thus, interaction between molecules is negligible, and we can assume that they move freely in straight lines according to Newton's first law. However, occasionally they come close to each other, experience intermolecular forces, and their velocities change. These interactions are called collisions. Molecules collide incessantly against each other or with the walls and change their velocities. The collisions are considered to be elastic. We can derive an expression for the pressure of a gas based on the kinetic theory. So let us derive. Before that, let us assume certain standard assumptions. The first assumption is the molecules of a gas are identical, spherical, and perfectly elastic. Elastic means when they hit the walls of the container, they come back with the same velocity using Newton's law. The volume of molecules is negligible in comparison to volume of the gas. Molecules of a gas moves randomly in all directions. The speed of a gas of the gas molecule lie between 0 and infinity. Their collisions are perfectly elastic. Sixth assumption is the number of collisions per unit volume in a gas remain constant. The number of collisions per unit volume remain constant. No attractive or repulsive force acts between gas molecules. Now we will take up ideal gas equations. The equations which relate pressure P, volume capital V, and temperature T of the given state of an ideal gas is known as gas equation. Now we will define some constants. That is, the first is universal gas constant capital R. The universal gas constant signifies the work done on by or on a gas per mole per Kelvin. Its dimensions are m, L to the power of 2, T to the power of minus 2 and theta to the power of minus 1. The standard temperature and pressure value is under STP, the value of R is 8.31 joules per mole per Kelvin. If we want to express the same in terms of calories, then its value is 1.98 calories per mole per Kelvin. Next is Boltzmann constant, small k. It is also represented as small k subscript b, kb. Its dimension, Boltzmann constant's dimension is m L to the power of 2, T to the power of minus 2 and theta to the power of minus 1. So it has got mass, length, time and temperature. Theta is temperature. So K is small, the value of K is found to be K is equal to 1.38 into 10 to the power of minus 23 joules per Kelvin. The kinetic theory of ideal gas, the equation is different for different conditions. So let us quickly summarize these equations. So if we consider 1 mole or Na molecules, N into A molecule or m grams or 22.4 liters of a gas, then the equation is PV equals RT. In the second case, if we consider mu mole of a gas, then PV equals mu into RT. If we take one molecule of a gas, then PV is equal to R divided by Na into T, or that is equal to R by Na is K, small k into T, where K is the Boltzmann constant. For n molecules of gas, PV is equal to N into Kt. For 1 gram of gas, PV is equal to R divided by m into T, that is equal to gamma into T. For n grams of gas, PV is equal to N into R into T. So this you please remember. Different forms of the equation because we are using these equations interchangeably. Now, derivation of an expression for pressure exerted by an ideal gas. Consider a gas enclosed in a cube with face area capital A and side of length capital L. Assume the motion to be x-axis. Please refer the diagram or the figure shown on the screen. Here x, y and z are three mutually perpendicular axes as shown in the figure. Here the velocity components will be in all the three directions, Vx, Vy, Vz. And when the molecule hits the wall and retards, the velocities in y and z direction remain unaltered. And x component changes by reversing itself from Vx to minus Vx. So the ordinates are written as Vx, Vy, Vz in forward direction, minus Vx, Vy and Vz in the reverse direction. Now we will calculate the momentum. The velocity has changed from Vx to minus Vx and momentum will be minus m into Vx. The change in momentum of the molecule along the axis is delta px is equal to minus vx minus m into vx. That is, summing up, it becomes change in the total change is minus 2m into vx. Let it be equation 1. By the principle of conservation of momentum, the momentum imparted to the wall in collision is 2m into vx, where vx is the velocity in x direction, m is the mass. Now we will calculate the delta t, the time taken to hit the wall and bounce back to the same position. Now the delta t is given by delta t is equal to 2L by Vx. You have to know that Vx, that is velocity into distance, is length. Therefore Vx delta t is equal to 2L by Vx, where Vx is the velocity in x direction. Now we will calculate the force. By Newton's second law, force is equal to momentum over the time. Therefore, that becomes delta P is 2m into Vx and delta T is 2L by Vx, and this Vx goes to the top numerator. So it becomes F is m into Vx square by L. Let it be equation 2. And if we consider N, capital N, as the number of molecules, total number of molecules, the average force is given by F average is equal to N into F, that is equal to N into M into Vx square by L. This, let it be equation 3. Hence, pressure by definition is P is equal to F average by area. Therefore, we have to divide equation 3 by area. So it becomes equation 3 for pressure becomes Nm into Vx square divided by Al. Let it be equation 4. As the gas molecules are in random motion and considering the motion in all directions, we can write it as the total speed of the particle is given by Vx square plus Vy square plus Vz square, or Vx square is equal to Vy square is equal to Vz square, that is equal to 1/3 of V square. Let it be equation 5. So therefore equation 4 becomes P is equal to Nm into, instead of Vx square we will write V square divided by 3 into A into L. Let it be equation 6. Therefore, taking average speed as V square is equal to V1 square plus V2 square plus V3 square divided by N, that is in all the three directions, we get P is equal to Nm into V square, V average. You see the difference between 6 and 7 is V average square divided by 3 into Al. That is equal to N into M, V average square divided by A into L is volume. So P is equal to Nm into V average square divided by 3V. Here the denominator V is the volume and capital V in the numerator is the velocity. Please note the difference. Or we can write this equation 7 as cross multiplying P into V is equal to Nm into V average or V square divided by 3. Or we can write P simply and substitute capital N by small n, where n is the total number of molecules per unit volume. When unit volume means V is equal to 1. Therefore, P is equal to small n into small m V square by 3. Let it be equation 8a. Here, in this equation 8a, capital N into m is the total mass and n, small n is the number of molecules per unit volume. We can also write it as 1/3 of rho, that is 1/3 of rho into V square, where rho is the density, that is total mass over volume, is P is equal to 1/3 rho into V square. Let it be 8B. Now we will calculate in terms of kinetic energy. We know that kinetic energy is given by the equation kinetic energy is equal to half into mv square. That is, v square is the velocity square. Therefore, the equation 8 can be written as we can write mv square as 2 times kv. So the 8v square here in equation number 8 can be written as 2n into kinetic energy divided by 3v. That is 2 by 3, 2 times kv divided ke, kinetic energy average. Or cross multiplying, we can write P into V is equal to 2n by 3 into kinetic energy average. Let it be equation 10. Here there are some remarks on the derivation. First, though we chose the container to be a cube, the shape of vessel really is immaterial. For a vessel of arbitrary shape, we can always choose a small, infinitesimal or planar area and carry through the steps above. Notice that both capital A and delta T do not appear in the final result. Please see here. The area and the delta T does not appear. By Pascal's law, pressure in one portion of the gas in equilibrium is same as anywhere else. Second, we have ignored any collision in the derivation. Though this assumption is difficult to justify rigorously, we can qualitatively see that it will not lead to the erroneous results. Next, we will calculate the kinetic interpretation of temperature. Kinetic interpretation of temperature. We know from the equation 8 PV is equal to Nm into V square divided by 3, which can be written as PV is equal to 1/3 small n into V. V is the volume, m into V square. That is 11a. Let it be equation 11a. That can be written as PV is equal to 2/3. mv square is 2 times kinetic energy, or we can multiply and divide by 2. Therefore, 2 in 2 by 3, here 2 by 3 into capital N, in this capital N, 2 by 3 equals 2 by 3 into capital N into this term we will have it as half mv square. That is equal to 11b. That is multiplying with 2 and dividing by 2, and all other items are same as this equation. Therefore, in this equation, small n into V is the number of molecules in the sample. This is small n into V is the number of molecules in the sample. The quantity in the bracket, that is n into V, is the average translational kinetic energy of the molecule in the gas. Since the internal energy E of the ideal gas is purely kinetic, E is equal to n into half mv square. So equation 11 gives PV is equal to 2/3 of energy, total energy. That is n into half mv square we are substituting as E. Therefore, P is equal to 2 by 3 E. Let it be equation 13. Substituting PV is equal to Kb into Nt, that is universal gas equation. PV is equal to KB, ideal gas equation, KB into NT. We get KB into NT and the left hand side equals 2/3 of E. That is from equation 13. That equals we get E is equal to, here E we get 3 cross multiplying 3 by 2 into KB is the Boltzmann constant, is N is the number of molecules into T, capital T. Let it be equation 14. Or we can get, again rewriting, we get E by N, or cross multiplying E by N is equal to half of mv square. E by N is equal to half of mv square. That is equal to 3 by 2 into kb into nt. So n gets cancelled. N is taken to the denominator. Therefore, E by N is equal to half mv square, that is equal to 3 by 2 into kb into t. Let it be equation 15. Please write the equation and do it yourself. There is nothing, only rearrangement and separating the term E by N. That is, the average kinetic energy of a molecule is proportional to the absolute temperature of the gas. So here the average kinetic energy E by N is proportional to the term temperature of the gas, capital T. Now we have derived this expression for interpretation of temperature for an ideal gas. For a mixture of non-reactive ideal gases, the total pressure gets a contribution from each gas in the mixture. Therefore, equation 11 becomes P is equal to 1/3 of Nm small n Nm N1 M1 V square plus N2 V2 square plus etc. etc. Let it be equation 16. That is this equation. Therefore, in equilibrium, the average kinetic energy of the molecule of the different gases will be equal. Therefore, half of M1 V1 square equals half of M2 V2 square. This is the kinetic energy is equal. That is, we have found out to be 3 by 2 kb, that is Boltzmann constant into T. This is from equation 15. Therefore, so that P is equal to N1 plus N2 plus etc. etc. into kb into T, which is the Dalton's law of partial pressures. Hence, we have also derived an expression for Dalton's law of pressure. Next, we will have some more relationship and take an example to understand the concepts of kinetic energy and kinetic interpretation of temperature. We know from the equation 15 that E by N is equal to half mv square, that is equal to 3 by 2 into kb into T. This is from equation 15. We can get an idea of typical speed of molecule in a gas. Let us take an example. T as 300 Kelvin. The mean square speed of a molecule in nitrogen gas is small m by m of N2 divided by N of argon. That is equal to 28 by 6.02 into 10 to the power of 26. That is equal to 4.65 into 10 to the power of minus 26. So V square will be equal to 516. Simplifying, we will get 516 m square into s to the power of minus 2. Therefore, the square root of V square here is known as the RMS speed. RMS speed and is denoted by VRMS. Therefore, VRMS will be equal to 516, taking the square roots both sides. The speed is of the order of speed of sound in air. It follows from equation E by N is equal to half mv square is equal to 3 by 2 kb into T that at the same temperature the lighter molecules have greater RMS speed. Next lecture we will take up kinetic theory only part 2 where we will discuss law of equipartition of energy, specific heat capacity, mean free path, and we will answer questions 1 mark and 2 mark. Till then, goodbye.